Okay, folks, I want to work out an example could be from 4.1. So I kind of made up this function, but what we want to do is find mins and maxes, all right? So we looked at a few examples together in class. This is going to be one where we're going to use two different types of critical numbers. We're going to look for where the derivative is equal to 0, which means that the graph is flat, and so something like that or like this. And so if the graph flattens out, it has the potential to be a minimum or a maximum. We've seen it doesn't necessarily have to be, so graphs can flatten out and then turn and continue on in their direction. So it need not be a minimum or a maximum, but they give us potential mins or maxes if the derivative is equal to 0. The other type of critical number that we might find is if a derivative does not exist. So if the graph has something that looks like that, which you might call a cusp, then we can't really speak about the derivative at that point. We would say this function is non-differentiable at that point. You can't really draw a tangent line, a straight line approximation at that point. You could draw a lot of different straight lines that touch that at one spot, but none of them really approximate what's going on at the graph. So at those little sharp cusps or any type of sharp corner like in an absolute value graph, at points like that, we're going to say if that's what the original function looks like, we'll say the original function is not differentiable at that point. To say it's differentiable or non-differentiable means does the derivative exist. So if you're not really familiar with the graph, how do you know? Well, we can consider the domain of our function, and then also once we take the derivative, we can ask ourselves, what's the domain of our derivative? And if there was x values where the function was defined, but then our derivative becomes undefined at those values, then that's probably what's going on over there, is we've got some kind of anomaly in the graph or cusp or something like that. So we'll just dive in, take the derivative, and then explore that. First of all, though, this function f, the domain of this function f, my original function, is all real numbers. So let's talk about why that is. So I've got a product here. So I've got a product of two functions. 4 minus x squared is a polynomial. That domain is all real numbers. X to the 2/3, not considered a polynomial because of that fraction power. So that 1/3 power is actually a radical. But it's a power function. Domain is all real numbers. If I have a x to the 1/2 power, right, that's the same as square root. And if you want to draw a little 2 there to emphasize that you've got a square root, you can. Usually we don't see that. Square roots, we can't take negatives, right? So this domain is not all real numbers. But if you've got a 1/3 power, right, which is a cube root, now I can take the cube root of positives and negatives, right? The cube root of a negative becomes a negative. Cube root of 0 is okay. So the domain of x to the 1/3, which is a cube root, is all real numbers. And then if you've got 2/3, that's the same as taking this and then squaring that. Still all real numbers, okay? So our original function, his domain is all real numbers, negative infinity to infinity. Why do I even care about that if I want to jump in and deal with the derivative? Well, once I look at the derivative, if the derivative is undefined at a point, as long as the original function is defined, though, then that means there's a point that lives on the function. And then so it does have the potential to be a minimum or a maximum. If the original function is undefined and then its derivative is also undefined, you might look at the behavior, maybe I'll look at an example like that towards the end. You might look at the behavior on either side of that value to see if I'm increasing versus decreasing. But if the function doesn't exist and there's no point there, then that lack of a point couldn't become a min or a max. So we want to consider where the function exists. The function exists everywhere. So any point along this domain is sort of fair game as far as being a extreme value, a min or a max. So now let's look at the derivative. So let's find the derivative of this. This will be an exercise because we've got a product here. So I've got to use my product rule to get the derivative, okay? So let me just step through my product rule. We know product rule is one of the original functions times the derivative of the other function and then plus the opposite scenario. So let's say the original first function, so 4 minus x squared, times the derivative of the second function. Let me do step by step just to demonstrate what we're doing. Times the derivative of the second function, x to the 2/3. So as I've emphasized in the past, I haven't taken the derivative yet. I'm sort of just indicating that I will take the derivative of that. Plus, let's say the second function, x to the 2/3 power, times the derivative of the first function. So times d dx of 4 minus x squared. So at this stage in the semester, do we really need to show that? Not necessarily, but is it nice if you've got that in your notes? Yeah, maybe, because you're showing that we're using the product rule. You're showing step by step what's going to happen. Next thing we'll do is now take those derivatives and then maybe combine some like terms, see what we've got. So what we're looking at here is 4 minus x squared times the derivative of x to the 2/3 power. I'm going to use my power rule here. So 2/3 is going to come down as a coefficient. So we're going to get 2/3 x and then raised to the 2/3 minus 1, 2/3 minus 3/3 is going to give us a negative 1/3. Okay, and I'll clean that up momentarily, but let's finish our process. So plus x to the 2/3 times the derivative of 4 minus x squared with respect to x. I've got a subtraction, so we just go term by term. Derivative of a constant is 0. Derivative of x squared is 2x, and then I'm subtracting that, so we're going to get a minus 2x. Okay? So that's our derivative. Let's clean this up a little bit, sort of in place. So here, I've got 2/3 is a fraction. X to the negative 1/3. That x technically lives up top with the 2 at this point. I'm going to move it to the bottom so I can create a positive exponent. So I'm going to move x into the bottom with the 3 raised to a positive 1/3 exponent. Okay? And if you want to call that a cube root, you can do that. If you want to keep it as a 1/3 power, you can do that. So let me clean this up a little bit. This thing lives over 1, right? So anything is always itself over 1 times this fraction. So that means multiply the top by the top, multiply the bottom by the bottom. So let me kind of combine these terms right here. The only denominator is going to be this 3x to the 1/3 power. And then I've got the 2. So let me put the 2 out front here, and then I've got 3, and let's just say cube root of x is my x to the 1/3 power. All right, so I put the 2, the 3x to the 1/3 power down here, being multiplied by that 4 minus x squared. Could I distribute this 2 into there? I actually could, because the exponent is on the x, but let me leave it alone for now. And then what am I doing over here? Combining this term, I've got x to the 2/3 power, and then here x to the 1st power, right? And this is all being multiplied, so I'm adding it. But then I'm multiplying x to a power times a negative 2, and then times another x to a power, x to the 1st power, which I could call 3/3 if we want to, okay? And so I can actually tie these guys together. X, same base. If I add those exponents, I'm going to get x to the 5/3, okay? And then I've got a minus 2. So let's, I'm subtracting from here, minus 2x to the 5/3 power, okay? Since I've got fraction powers, and I'm probably going to want to get a common denominator here, let me actually revert back to the fraction power here, x to the 1/3, and that will help us get our common denominator. Okay, so what we've just done here is take the derivative. We had to use the product rule. I still want to clean it up a little bit further. But let me kind of pause, go piece by piece. So if the whole exercise here was just take the derivative, I would probably claim you could be done, right? You might want to be done here. Do I need to get a common denominator and tie these guys together? Debatable, maybe not for a final answer. However, what we're going to want to do is find critical numbers here. So our critical numbers are going to be where the derivative is equal to 0 or where it doesn't exist. I've got an x in my denominator now. The original function domain was all real numbers. Everything was good. But now I've got x's in my denominator, and x, which means certain values, particularly 0, seems like it might be problematic, right? If 0 to a power is still 0, 0 in the bottom, 0, bad. Once I get a common denominator here, that's still going to be, I'm still going to have that problem. So in other words, I can identify that problem without getting the common denominator. However, when I find the other type of critical number, when I set my denominator equal to 0, that's going to be easiest. That we're going to have the easiest time doing that, I think, if we get a common denominator first, which is not going to be so bad, okay? Since I've got to get this common denominator, let me just do that. So I want to subtract these guys, so this is itself over 1, and I'm going to kind of extend that fraction bar so I have stuff to multiply by. So I'm going to multiply top and bottom here so I can get my common denominator. All right, so that 1 I put down there as sort of a placeholder, but 1 times whatever. So this denominator has 3x to the 1/3, so I need to incorporate that to top and bottom here so I can do my multiplication. So let's multiply 3x to the 1/3 power down there. And up here, you might have been saying, what's a 5/3 power, right? That's kind of weird. But what am I going to do now? Multiply top and bottom by that same quantity. And now I've got the same base, what I did earlier, same base. I can add those exponents. And 5/3 and 1/3 is 6/3, which reduces to 2. So we're actually just getting an x squared up there. So that's not so bad. So this is what I'm multiplying to get my common denominator by that purple. Let's clean this up. So 2 times 3 is 6. As I just said, x to the 5/3 times x to the 1/3 is going to be an x squared. So that numerator actually cleans up quite a bit, just to 6x squared. And then now I've got this denominator, 3x to the 1/3. And so if I'm doing this on paper, pencil and paper, I'm probably writing equals, 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 and doing one line to the next, to the next, to the next. With the board, I'm kind of erasing a little bit, trying to clean up as I go. Once you get the common denominator, right, if I've got a over b and I'm subtracting c over b, well, once you've got the common denominator, that means just subtract those numerators, right, over the same denominator, all over b. Right, so I'm just going to do that right now, just kind of tie all this guy together over this common denominator. So that was a subtraction. Here's our big fraction bar. And I'm over 3 to the x to the 1/3 power. The fraction power was helpful here to tie those guys together. That's why I went back to the fraction power. You can really do it either way right now. If you like fraction powers, fine. Fraction powers are helpful if you're going to like take later derivatives, go further. You want sort of numerics right there. Yeah, the original function had a fraction power, so there's nothing wrong with it. So that's fine. Okay. And is there anything else I can do? So at this point, I was debating distributing, or earlier I was debating distributing the exponent. Now I want to, because look what we ended up with. We ended up with another x squared term over here. And so if I can't combine this x squared with this x squared yet because of this multiplication, right? So our PEMDAS order of operations, I have to deal with the multiplication before I can deal with a subtraction. So let's go ahead and distribute that too. So 2 times 4 is going to give me 8, and then I'm going to have minus 2x squared. So this gives me 8 minus 2x squared, just replaces that, and then minus 6x squared. Let's combine those, right? So minus 2x squared minus 6x squared altogether becomes minus 8x squared, and that's all over 3 x to the 1/3 power. Okay. Wow, that really cleaned up, right? It was a mess, sort of, and then now that looks nice. So let me erase the power rule that we used to find this derivative and just list our derivative right there. And could I do anything else at this point if I want to clean it up a little bit? Maybe I can pull out an 8 from the top. Factor out that common 8, and then I have 1 minus x squared. That's nice. Nice difference of perfect squares, factors easily. And that's all over 3x to the 1/3 power. Okay. Can I do anything with those x's, try to combine terms or anything like that? No, I cannot. And why not? Because that x is tucked inside parentheses. These x's are not in parentheses. So, yeah, so that's my derivative. Okay. So, that itself was an exercise, right? We could be exhausted right now and then want to be done because we had to use that product rule. Kind of complicated to simplify. However, we're looking for mins and maxes, right? We're in section 4.1. We want to identify extreme values. So we're still going to use a derivative test now. All we did was just get our derivative. First of all, and again, this is, WebAssign probably won't be asking you for this, but I just like to emphasize it. Practice expressing domains, thinking about domains, using interval notation. What's going on here? Are there any x values that became problematic? The original function was fine. This function, 1 minus x squared. So sometimes when folks are dealing with domains, let's think about if x is 0, then the denominator is 0. And you can't divide by 0, right? That's a no-no. We can't divide by 0, so 0 is bad. Some folks have that in their mind then, that anything that makes a 0 appear is bad. And they might say, well, wait a minute, 1, right? If I do a 1 up there, 1 minus 1 is 0. Then I'm getting 0 over, right? But if you do 1 in here, then you're going to get 0 over 3, which is equal to 0. That's okay. That's actually something that's one of our critical numbers then, right? Because if plugging 1 in here makes the derivative 0, that means the graph is relatively flat there. That means we've got a scenario potentially like something like that, right? So we're not going to say 1 is bad or negative 1 is bad, but just because we get a 0 up top. 0 up top is good, right? 0 in the bottom is undefined, and so those become the problem values. So the only problem x value here is when x is 0, so the domain is all numbers other than 0. Okay. So while I almost said X files for some reason, while WebAssign won't make you probably write this in domain notation, interval notation, knowing what we know here is that essentially this is telling us the derivative doesn't exist, right? Another way of kind of capturing that idea is f prime of 0 does not exist. And so that's the type of critical number now. That means that if the derivative doesn't exist, the original function does exist though, right? F of 0, we get 4 minus 0 squared times 0 though, so we get 0. So f of 0 is 0. So the function exists at 0, passes through the origin. It's just not differentiable there. So maybe we've got like a sharp corner or a cusp, right? But that's got a sharp corner has the potential to be a minimum, just like a flat portion has the potential. Okay, so we're in good shape. So I'm kind of putting the cart before the horse right there as far as finding critical numbers. So step by step, if you're doing a problem like this, you're given a function. So step 1, find its derivative. Step 2, find critical numbers. So find or list critical numbers. Okay. Some books call these key numbers or something like that. Critical numbers are x values where we have the potential for a min and a max. So where f prime of x equals 0, or where f prime of x does not exist. Okay, so we have two types of critical numbers that we might find. Here we found one. F prime of 0 does not exist. So critical numbers, let me list them over here. Critical numbers, 0, right? And let me just put here f prime of 0 dne, even though I've got it written right above. And this is, so now to find the other types where your derivative is set equal to 0, what we want to do is set that derivative equal to 0, right? And solve for x. So you can try doing that. The reason why I wanted to get the common denominator, remember, and kind of unite all those crazy terms, is because now solving for the x that makes it 0 is relatively simple. As I mentioned earlier, a fraction is 0 if and only if the top is 0, right? And the bottom should be non-zero, so we want to check that out. But the top, so we can set the top here equal to 0 and try to find those x values. We could divide both sides through by 8 to get that out of the way. So that what that does is here 8 over 8 cancels out, so I'm left with just 1 minus x squared, and 0 over 8 is still equal to 0, right? So we've got that. Here you've got a difference of perfect squares, so if you want to try to factor, you can go ahead. 1 plus x, 1 minus x. I think we're used to this, so if you just look at this, I've got some other critical numbers, right? If x is 1, 1 minus 1 is 0, 1 squared, and if x is negative 1, squared becomes positive 1. So we're going to get negative 1 and 1 are other critical numbers. And just so for myself, I'm kind of keeping track, f prime of negative 1 equals 0, f prime of 1 equals 0. Okay? So sometimes some books call this a type 1 critical number, right, where the graph is flat. Saying the derivative is 0, I interpret that as the graph is flat there momentarily. When x is 0, the other type 2 critical number, where the derivative doesn't exist, so the graph is like sharp there, right? It's got some kind of sharp corner. Okay, rolling right along. So we found our derivative, step 1. We found our critical numbers, which is step 2. Step 3, let's set up a number line, put those critical numbers there, and test values. All right, that just becomes some calculations, and then we draw our conclusion. So we're almost done. So let's put our critical numbers here. All right, and so I've got 3 numbers on the line. So I've got 1, 2, 3, and 4 intervals to deal with. Okay. I can get rid of these domains. I guess they were on my mind for a moment. Let's discuss even versus odd functions. So if you've got that intuition, or if you were good at that back in pre-calculus, let's think about what's going on. Our original function f, 4 minus x squared, that itself is an even piece, right? In other words, the only thing you're doing to x is squaring it. So this x, if you plug in a minus 3 or a plus 3 and square it, you get 9 either way. So this portion treats positive and negative versions of the same value identically. This thing also does that, because remember I manipulated this guy before. I could think of this as x to the 1/3 or cube root of x squared. And so that squared nature is again treating positives and negatives the same. So that means this function f is what we call an even function, which means it has y-axis symmetry. So our original function is going to be symmetric. The derivative is going to be an odd function. How do we see that? Well, here the top again, this portion is even. In other words, this treats positive and negative values exactly the same. However, x to the 1/3, our cube root right there, treats positives and negatives the same except for their value. In other words, 8 to the 1/3 power is 2. Negative 8 to the 1/3 power is negative 2. Right? So we just get the negative of those things. Why is that valuable? I have 1, 2, 3, 4 tests to do, right? If I can use that symmetry, then I've only got 2 tests. Because in this case, since 0, I've got, in other words, let me try f prime of 2. So I'll test this value 2. Sometimes I don't like to put that on a number line, and I'll explain why. But I want to do f prime of 2. And let's calculate that. Sometimes the reason why I don't want to put this on a number line, do I want to say that now? Let me find f prime of 2, and then we'll explain. F prime of 2, so let's plug it into the derivative. So 8 times 1 minus 2 squared. 2 squared is 4. 1 minus 4 is going to give me a negative 3. Okay, so I'm trying to cut the work down a little, showing-wise. 2 to the 1/3 power. What am I going to call that? It's just cube root of 2. 3 times the cube root of 2. You want to see what's cool about this stuff now is, what is cube root of 2? Do I have to break out a calculator? I don't really care. All I care about is the derivative. Is the graph increasing or decreasing right here? In other words, is the derivative positive or negative here? 8 times negative 3, positive times negative up top, gives me a negative numerator, right? 3 is positive. Cube root of 2, cube root of a positive number is positive. I don't know exactly what it is, right? Some irrational number that goes on forever decimal-wise, but positive times positive gives me a positive. Negative divided by positive is negative. Right? If you take a negative number divided by a positive number, you get a negative number. So do I need to actually calculate this? No. If I was trying to write the equation of the tangent line at that point, then I would need to know exactly what its slope was. I'd want another derivative. But all we care about here is positive versus negative. So if you find yourself doing stuff like this, that's fine. So f prime here is negative, okay? Which means the original function, f, is decreasing, right, on this interval from 1 out to infinity. Okay, depending on, different books do this differently. So when I've taught Math 26A, which is for just other majors, other students than you, but need a calculus class. There's no trig in there. In that textbook, they have a whole section devoted to increasing and decreasing functions. That's like section 1, and then they do maxes and mins, right? Because we're kind of tying those ideas together. In other words, we're looking for increasing then decreasing, tying that together as far as to locate a maximum in this case. However, at this point, there's other intervals to consider, but I might say f is decreasing on, and this might not be the whole story, because again, it might be decreasing on one of these intervals, but it's definitely decreasing for on this interval from 1 out to infinity. All right, and we use round brackets because at that very moment, I think we're going to show it's a maximum. It's not really doing anything at that moment, but on this interval, it's always constantly decreasing. Yeah, so we can write statements like that. What I notice sometimes is if you start, so I put the critical numbers on my number line. If you start marking up the number line with the test values, students end up conflating those test values with the endpoints of your intervals, and it just becomes real busy. So the way I do it is kind of within that interval, a little bit below, I show the test value. It's clear that I'm testing 2 because it's written right there, but maybe I won't mark up the line too much. You do your own style, whatever, but that's okay. So got that. All right, there's a couple more intervals to check. However, let me just jump over here and let me show the symmetry of what I'm talking about here. All right. In other words, let me do f prime of negative 2, because I claim this guy came out negative. I claim the answer is going to be positive, and I don't need to. I will show it, but I claim I don't need to. I could do that, but I could say this is positive because this guy's an odd function, so it's going to have opposite behavior right there. Okay. But how do I know that? Well, let's think about these calculations that happen. 8 times 1 minus negative 2 squared, right? So the top doesn't care about positive versus negative, treating everybody the same. Negative 2 squared is still positive 4, and then 1 minus positive 4 is still negative 3. Okay, so nothing happened up top different. Nothing different happened. The top is still negative. However, the bottom now is this constant 3 times the cube root, and again, I'm treating it like cube root. Let me show that. But the cube root of a negative, so now I've got cube root of negative 2, okay? 3 is positive, but positive times cube root of a negative is a negative. And now, so positive times negative becomes negative, right? So the denominator changed, but now negative divided by negative becomes positive. So the overall result changed as well, all right? If you calculated it, you'd see that it's the exact same number, right? Because you get negative 24 as your top, negative 24 is your top. So you got the same thing that you're dividing by. You're just still dividing by your 3. And then cube root of 2 and cube root of negative 2. Here I did cube root of 8 and cube root of negative 8. Kind of claim that we get the same magnitudes right there. Anyway, if you want to try to use those symmetries, go for it. It's helpful if you can. And in this case, we've got symmetric intervals going on. Anyway, let's clean this up or button this problem up. So f prime is positive, which means f is increasing. All right. And so there, draw a little arrow. Okay. Typically, I don't jump around like that. I typically start with the larger intervals. Why? Because it's usually a positive number, so calculations are easy. And then I step backwards, step to the left. But since we knew this one, and because of symmetry, I might as well jump over here. But typically, I'll go back one at a time and see what's happening at that critical number. So let's test something in here. Okay, so f prime, I usually would show my tests again. I'm on the board so I can erase stuff. We're recording it so you can rewind. But in your book, of course, leave all your, or on your notes if you're showing this, your work, show all the tests, right? Show them all simultaneously. I erased a couple. F prime, I've got to choose a number between 0 and 1. Do I have a great choice? I don't know, 1/2, right? Anything really. If you like decimals, you can use decimals. I always stick with fractions most of the time. So here we've got 8, and again, all I care about is positive or negative. I don't care about the value. So then I've got 1 minus 1/2 squared is 1/4. So 1 minus 1/4. And then that's over 3 times the cube root of 1/2. Okay, so let me just kind of talk my way through this result. 1 minus 1/4 is 3/4, which is positive. And then positive 3/4 times 8 is positive. So I have a positive numerator. Cube root of a positive number is positive times positive 3 is still positive. And positive divided by positive is positive. Okay, cool. So we get f prime is positive, which means f is increasing, which means the function's going like that. And so we increased, we stop in a moment, we turn around and decrease. So what did we find? A maximum, right? Simple as that. So at 1 here, let me just put max, because we've identified that. Let's see what's happening over here. So I would do f prime of negative 1/2, okay? So I claim it should be negative because of the fact that that doesn't always happen with every function, but this derivative happens to be odd, happens to have that symmetry, so it's going to happen. If you don't believe it, just calculate it again. We'll have 8 times 1 minus negative 1/2 squared is still positive 1/4. Right, so we still get that. So same identical numerator. We've got a positive numerator here. Denominator 3 times cube root of a negative number, right? Negative 1/2. And cube root of a negative is a negative. Negative times positive is negative. Positive divided by negative is negative. Okay, so we got the opposite behavior here. So f prime is negative. F is decreasing. And so it looks like that. Okay, let me erase this derivative. It's in my way. And let's draw some conclusions now about the behavior of this graph. So moving from left to right, we're increasing until this point, and then we turn around and decrease, right? So if you're increasing and then turn around and decrease, we found a max. So this function has a max at negative 1, right? Then it's so following in this interval now, it's decreasing, and then it turns around and increases, right? So that means at 0, it had a minimum, right? Wait a minute, the derivative didn't exist. Does that mean we can have a minimum? Sure, right? It's still, the function's going down. Remember, the original function did exist. That means we can still have a minimum. And then if we're decreasing to a point and then increasing, and the function, the derivative doesn't exist, then we found like a cusp or some sharp little edge like that. Okay, so we found the minimum now. And then we already talked about over here. We increase then to a certain spot, turn around and decrease, so that represents a max. Beautiful. So we're good. Okay. So I'm going to erase this stuff again. This would probably be like a one-page paper, one-page result, showing all the work, especially if you want to build the graph after. Let me erase all this stuff and let's talk about how we might build the graph together. So really the goal of this section, this whole chapter 4, is kind of two goals. Using this idea of maxes and mins, eventually we will incorporate that into word problems, right? Let's say you've got a function that describes your company's profit as you build a certain amount of computers. Then the more computers you make, the more money you can make because you can sell more, right? Until a certain amount, and then you've made too many and they're not selling, now you've got overstock, right? So if you make too many, now your profit starts decreasing. So where is how many should you build to maximize your profit? Use a derivative, right? So that's one application of why we care about mins and maxes, is for real world applications. Another one is to build graphs of functions without Desmos or without a calculator. Just build the graph. And so we want to know where the extreme values happen for that. Okay, let me just make a little, I could do function notation, or let me just make a little table. Let me put my critical numbers in here, -1, 0, and 1, and just calculate the function values. At least I have 3 points then to plot. And I can get a decent sketch out of the graph then. F of 0 is 4 minus 0, so 4 times 0, so we get 0. Okay? F of 1 is going to be 4 minus 1 squared, so 4 minus 1, so 3, times 1 to the 2/3 power. So 3 times 1 is 3. All right, so we're just going to get 3 for that function value. And I claim 3 for this function value. Again, using symmetry. F is even. Right? If you want to square -1 and do that, you can do the same thing. But there we go. So let me just do a rough, or start plotting this. So let me come over to 1 and back to the left to -1. And let me go up 3 units. 1, 2, and 3. Okay? So what can I plot here? Well, I know that I've got the point 0, 0, so the origin lives on this graph. At 1, I'm up to the height of 3. And bear with me guys, this video is getting a little long. Let me just shrink this 1, 2, 3, just so I don't have to reach too much to show what's going on here. So I've got 1, 3. I've got -1, 3. Okay? Now, so those points live on the graph. Let me do the rest in green, maybe, and then maybe outline if you can't see it. At this point, I care about what's going on. So I could plot extra values, right? So a real nice way of doing this might be choose a point between these and plot it to kind of see how high I go. Choose a point after this to kind of see how high I go. Maybe find other x-intercepts. So that might be something interesting. Set f of x equal to 0. Set your original function equal to 0 if you want to graph it. And so if you've got a function equal to 0, then I would have this. 4 minus x squared times x to the 2/3 equals 0. Okay, I've got a product equals 0. That only happens if this term, 4 minus x squared equals 0, or if this term, x to the 2/3 equals 0. This one yields 0, which we already found because that was a critical number, because that was one of our extreme values. We already plotted that one, so we've got that right there. This thing's the difference of perfect squares, and so you're going to get x is 2. I almost put 2 over 2. Let's say plus or minus 2. All right, and so we've got that. So I can actually go a little bit further. That's not an extreme value, meaning a min or a max, but x-intercepts, think about how you would graph back in pre-calc before you had mins and maxes. You would pretty much just plot intercepts, right, and then find some points in between. All right, I see on the screen, for some reason, I think it's the angle of my computer making that point look a little bit higher than this one. But okay, so yeah, so let me plot a few more points. I will use green again just to emphasize the difference between my extreme values and then these intercepts. So again, do we really have to do this? If you want to go further and make a nice graph, I would say look for intercepts that you can. So we have the origin and 2 and -2. So that means the function actually lives here and here as well. Okay, again, not extreme values, so the function's just going to pass right through those, but that gives some stretch, right, instead of just tapering off. Let's figure out what we knew. The derivative at 1 and negative 1 was 0. That means it was nice and smooth. Picture the top of a parabola or the bottom of a parabola. So I kind of cheat a little bit. I exaggerate what's happening for the sake of drawing a smooth function. A problem with the way students graph sometimes is they found maxes, they found mins, and now they do this. Right? They draw something like that, and they say, you know, connect the dots, whoop-de-doo, I have that. Except what we've shown now is this looks like a cusp up top, and I know I'm doing the light green, so you can't really see it. But in other words, it doesn't hit the max and come down like that, right? Because the derivative wasn't do not exist there. The derivative was 0, which means it wants to be nice and smooth up top, like a nice smooth hill. Picture of parabola. So the way I accomplish that with a graph, and it's a little bit easier with a kind of a marker with ink, because I can kind of smudge it a little bit, is I kind of exaggerate. The graph wants to be flat right here, right? So again, I'm kind of cheating. What I'm drawing is not really accurate. There's not like a constant portion where it's level for a distance. It's really just a momentary flatness. So what I'm doing there is really kind of graphing the tangent line a little bit, okay? But now that I have that, now I kind of use that and kind of smoothly come down, right? So I'm kind of exaggerating that. And so it's definitely round up there, all right? So I'm trying to keep that sort of roundedness like so. And so I start with the I almost feel like I'm painting or something, right? Like I'm like applying the paint up there in the straight line and then kind of like with a tool like smoothing it down or something like that. But I'm really trying to emphasize that it's not a cusp up there. It's a nice smooth transition, right? However, down here at 0, it is not a smooth transition, right? It does not go like that and sort of bottom out with a flat derivative. Because we did not find that the derivative was 0 there. We found the derivative does not exist. And that means we've got a sharp cusp. So for that one, I want to come down and emphasize the sharpness. Okay? And then again, this is just an intercept. So it's just going to pass on through there and go by. So it's not that that point is necessarily any more important than any other point, except it kind of anchors. How do I know it goes here and not like way over, right? So it kind of gives a little shape to our graph like that. All right? So let me get rid of this portion. Now that I did that in green, let me try to smooth it up now a little bit. So again, I want to come up from the sharp corner, nice and horizontal right there, turn, come down, fix that up a little bit, and so forth over here. There we go. And if I miss my green line a little bit, it looks okay. Okay, so kind of like a little McDonald's arches here, right? So nice, smooth, sharp. However, we've got a min and we've got a max, or two maxes. So it doesn't really matter whether or not we've got which type of critical number we have. They've both got the potential to be minimums and maximums, and then we just rely on that first derivative to tell us what's going on. All right, folks, very long example. I will leave that as the only example for now. But tackle the homework problems. Let me know if you guys have any questions, and onward and upward.